KBS Fest. And the first speaker this afternoon is Apoorva Khare, and he's from the Indian Institute of from IISC here in India, of course. And he will speak about moments in the history of positivity.
Yeah. Thank you very much for inviting me. It's a pleasure, of course, to be here, and many wishes, many happy returns to Professor Sinha. So I will talk about moments in the history of positivity, where, again, as he told me, moments has two meanings, and it does. So this is partly joined with Alex Belton, Dominic Guillot, and Mihai Putinar, and partly with Terence Tao. And the first half is actually somehow a history talk in some sense, more historical, and then I'll get to some of the recent work joint with these people. So just to set some notation, so all our I'll study matrices and functions acting on matrices. All matrices will be real and symmetric. So a matrix is positive semi-definite. I'll just call it positive. If its quadratic form is positive semi-definite, and there are several equivalent forms, of course, principal minors, eigenvalues, all being non-negative. So now what I want to do is I want to act by functions on matrices, but I want to act on them entry-wise, not on the spectrum, as one normally does maybe. This is maybe slightly less well-known / well-studied, but I want to tell you that it is quite well-studied. So given an integer n, given domain I, let Pn of I denote the n by n positive matrices whose entries, not eigenvalues, whose entries are in I. And now a function with domain I acts entry-wise on the matrix in the obvious way. Right? And the question that I'm interested in, and not just me, as I will tell you, is for which functions is it true that if you start with a matrix which is positive, the output, when you act by a function, it's positive as well. And this turns out to have a long history, so somehow this talk is going to start with Schur, who of course was a remarkably versatile mathematician, and it will also somehow end with Schur. So it will come back full circle. But so the Schur product theorem is the starting point of this journey, and it says that if you have two matrices which are positive, then so is their entry-wise product, the Schur product, if you will. And now this provides some answers to this question, because if I set B equals A, then I just get that if A is positive, then so is its entry-wise square, which means that x square works. X square answers this question. And now I can set B equals A dot A, so x cube will work and x fourth, and so every single monomial works. But now if I know that so A square is positive and A cube is positive, then A square plus A cube is positive. So of course sums and positive combinations will work as well. And so I get that all polynomials with positive coefficients work. And now again, if I know that matrices are positive, then the cone is closed under limits. So if I know polynomials work, then power series work, because those are limits of polynomials. So as a consequence, and this is again very, very old, this is an observation by Polya and Zigo, if f is power series, it's convergent, and all the coefficients are non-negative, then this works. And this works in all sizes. There is no restriction in the Schur product theorem on the dimension of the problem, so this works in all dimensions. And Polya and Zigo, in their book on problems and analysis, they ask if there are any other functions that work. Right? And this took some time to answer, and the answer is very happily no. These are all the functions that work. And this is a famous result by Schoenberg. And so Schoenberg proved that there are no other continuous functions that work. And in 1950, so 17 more years later, Rudin removed the continuity hypothesis. And Rudin, so this is their theorem: F preserves positivity for all matrices of all sizes, if and only if F is exactly of the form that Polya and Zigo told us about. Right? So it's a nice and happy ending to the story. So in the first part of my talk, I want to tell you how Schoenberg came to this theorem and where he got there from. Okay? And so first of all, a few observations. So Schoenberg's result is the harder converse to his advisor. So Schur was his advisor, or one of them. So the Schur product theorem and Polya Zigo just said 2 implies 1. Schoenberg proved 1 implies 2. This is for matrices with entries in -1, 1. But you can ask other variants. What about matrices with entries, just all positive entries? And that was worked out by Harkrish and Vasudeva in 1979. And in all these cases, the answer is the same. The preserving positivity in all dimensions is a very rigid condition, and it implies very strong properties about the function. Okay. I'll outline. So in the second half of my talk, I will outline some stronger versions of both Vasudeva's theorem and Schoenberg's theorem, and how to go about proving those. Okay, so let me then begin, as I said, with Schoenberg's motivations. So those come from metric geometry. So Of course, many of us probably know Schoenberg as the inventor of splines. He wrote dozens of papers about splines. He has work on totally positive matrices and variation diminishing properties and so on. He worked on positivity preservers, spherical harmonics, and he worked on positive definite functions. And that was actually a very hot topic in those days when he was working on this problem. So just to remind you, so the idea is a function is positive definite if you basically you look at it being positive definite on a space X. The space can either be a metric space, as it's here, or it can be a group, like an abelian group, or it can be maybe an inner product space like a Hilbert space. And then what you need is a kernel that takes two arguments from the space, gives you one real number, and then the function is supposed to act entry-wise on the matrix that you get out of that kernel. So for a metric space, the kernel you are using is the distance. So 2 points from the metric space, the distance gives you a real number. F is positive definite on a metric space. If you take any distance matrix from there, apply the function entry-wise, and that is positive semi-definite. Okay. You could work with positive definite functions on groups, which was traditionally how Wagner's theorem is stated. There the function is x inverse y, and the function is of course sort of conjugation invariant or something, some equivariance. You can work with Hilbert spaces, in which case the kernel is the inner product. Anyway, so all of those were sort of being studied at that time. So the question, as I said, I want to tell you something about how this whole thing began. And this whole thing began with the notion of a metric space. So this, of course, was a very, very classical concept, which is now used all over the place. So here is a sample result that Fréchet had proved. If X is a metric space with n plus 1 points, then it isometrically embeds into Rn with the sup norm. And if I think n is bigger than 3 or 4, then you can even go one lower, right? 1 dimension less, I think. So that it very naturally led to asking which metric spaces look like nature, which look like Euclidean spaces. Okay? And so that was the question that some people were interested in at least. And so here are 2 papers that provided some characterizations. And in the very next article in the same issue of the Annals, Schoenberg reformulated the Fréchet's conditions and these conditions using positive matrices. So the statement Schoenberg's theorem says, fix a finite set X with n plus 1 points, so a metric space. This embeds into R to the R, so there's a reason I use the letter R here, but not a smaller dimension. So it tells you when it embeds into Euclidean space and also what the smallest or best dimension is. If and only if this matrix, so this matrix which is obtained out of the distance matrix, but remember the distance matrix is n plus 1 by n plus 1, this matrix is just n by n. Okay? So if and only if this matrix is positive semi-definite and of rank R. So that the rank itself tells you the dimension of the Euclidean space in which it sits. Okay, so that was Schoenberg's result. Let me tell you one half of the proof. Suppose my space does embed into this space, into Euclidean space. Then I can identify the points with the Euclidean space points, and so the distance is just the L2 norms, the L2 distance. So if X does embed into this, then you just literally do the calculation, this square plus this square minus this square. That's this norm square plus this norm square minus xj minus xk, but I'm rewriting it this way. And now you all know a square plus b square minus a minus b square is literally 2ab. And 2ab in this case means you get the Gram matrix of some, you get some Gram matrix, and therefore that's positive semi-definite. And not only that, you know the rank of the space, so you know the rank of the Gram matrix, it's less equals R. And since we said that it doesn't embed in a smaller space, the rank has to be exactly R. So that's one half of Schoenberg's theorem. The other half is slightly more involved, but again, it's 1 page, not too long. Okay, so another observation, this particular matrix is positive semi-definite. That was Schoenberg's condition, remember, the characterization. If and only if the bigger matrix, this is now n plus 1 by n plus 1, and this is just a simple matrix minus d square. If and only this matrix is conditionally positive semi-definite, which just means that this quadratic form is PSD, positive, on a codimension 1 hyperplane. So on not the full space of n plus 1 dimensions, on a n-dimensional subspace. Okay? And so that sort of is how conditionally positive matrices at least sort of emerge from metric geometry. So I'm going to look at this setting again. So what does this really say? So what does Schoenberg's theorem say together with this characterization? It says that a metric space embeds isometrically in Euclidean space if and only if you apply minus x square this function negative x square entry-wise to a Euclidean distance matrix, you get a conditionally positive matrix. Right? So that's the observation here. Applying the function minus x square entry-wise sends any Euclidean distance matrix to a conditionally positive matrix. So of course, it's natural to ask, can I remove the word conditionally? Which operations applied to Euclidean or other distance matrices give you positive matrices, and those are exactly what I defined for you, the positive definite functions. So here is one example. The Gaussian kernel, as Schoenberg noted, is positive definite on all Euclidean spaces. The usual, e to the minus x square. Right? So Schoenberg showed this using Bochner's theorem, which was again exactly around that time that was being discovered, and the fact that the Gaussian is its own Fourier transform. Here is a slightly simpler proof. And again, I want to give you this proof because it can be written in this space. So, and it combines three very pretty observations. One is Gantmacher and Krein. They proved that generalized van der Waals matrices are totally positive. In other words, if you will, take a sequence of increasing positive bases, take a sequence of increasing exponents, and look at the base to the exponent. That's the van der Waals matrix. The determinant is positive. Okay? That's all. That was the result. Now you use a result of Polya, which says that the Gaussian kernel is, that basically proves this statement for R1. Why? Because if you look at what does it mean to be positive definite? Take a distance matrix, which is just mod xj minus xk, apply this function to it, you get this matrix entry-wise. The claim is this is positive definite. Why? Because, well, by using properties of exponents, if you will, it's this matrix on the left, the same matrix on the right, and this matrix in the middle. And now I claim that this matrix is actually a van der Waals matrix, right? If you take this to be yj, then yj to the xk is this matrix. So that's the determinant of this is positive. Clearly the determinant of the whole thing is positive. And if you take any principal minor of this matrix, it looks exactly like the same thing. So that has positive determinant. So as a result, you get the Polya statement from Gantmacher and Krein's observation. And finally, the Schur product theorem literally says, if you know this for R1, then you know this for RR. So it's just as simple as that. So anyway, so you can do this in many ways. So now what Schoenberg actually proved, so what he showed was that this function is positive definite on R1. What does that mean? It means if you take any finite set of points from Euclidean space, take the distance matrix, apply this function entry-wise, you get a positive semi-definite matrix. What Schoenberg actually showed was that this is actually an if and only if. If whenever you have a space, you take some finitely, if this function is positive definite on that space, then that space is essentially Euclidean. More precisely, what he showed was that these maps look at not just e to the minus x square, but look at e to the minus lambda x square for positive lambda. Right? And if this family of maps is positive definite on a metric space, then that metric space is Euclidean. And the converse is, well, the previous slide. And he proved it for RR or for R infinity, by which he called the Hilbert space, and that just means L2, of course. So Schoenberg was, of course, also interested in distinguished subsets of RR. In fact, the distinguished subset came first, and then the full Euclidean space came next. So I'm sort of distorting history to tell you this story. What about subsets? So Schoenberg explored this question for spheres. And for spheres, in fact, you can check that a single function being positive definite on a metric space characterizes the metric space being in a Euclidean sphere. Okay? And that function is called the cosine function. So here is the theorem. So well, let me tell you first of all the metric on the cosine. So if you take the Hilbert sphere, which is just the unit vectors in L2, or any subspace such as unit vectors in Rn or Rr, then you have a distance, right? You have the usual spherical distance. If 2 points are antipodes, the distance is pi. If 2 points are not antipodes, then together with the plane, together with the origin, there's a unique plane through them. Look at the angle that they make on the great circle, that's the distance. So now if you apply cosine to any distance matrix, well, since the distance is just arc cost, you get a Gram matrix. And that's why cosine is positive definite on all Euclidean spheres. Okay? That's just trivial. And also, of course, in a unit Euclidean sphere, what is the maximum distance you can have? It's pi, because it's always the angle distance. So that if you have any metric space that embeds in a sphere, its diameter must be at most pi. So you have two conditions. This function is positive definite, and the diameter is pi. And that is an if and only if. A finite metric space, he proved it for separable as well, but a metric space embeds isometrically in this if and only if cosine is PD and diameter is pi. Okay, and I just told you one half of the proof. Yeah? So there are some beautiful results in, I mean, just this very, very simple proofs, but it's very beautiful. And the whole point is all of this story is going towards the result I stated at the beginning, which functions applied entry-wise preserve positivity. So Schoenberg, that proof of Schoenberg's. Okay. So I'll just point out, so we wrote a survey article with Alex Belton, Dominic and Mihai on sort of this whole, the history of positivity, entry-wise positivity preservers, and that's available in the archive. I also sort of taught a course on this in IISc where I am currently, and those lecture notes have all the proofs of this as well. And those are on my website if you want to see the proofs or whatever. Okay, so I mean, you can also read the papers themselves. Okay, so what I just told you was Schoenberg characterized Euclidean space as well as spheres in Euclidean space in terms of either the Gaussian family or just the cosine. And at the same time, of course, there was this big rage about positive definite, positive definite functions. So after understanding that cosine is positive definite here, he was interested in classifying all the positive definite functions on spheres. Actually, more precisely, he wanted to understand which functions composed with cosine. F of cos of the distance gives you positive definiteness. And that's the main, that was actually in some sense the main theorem of his paper, the paper in which he proved the theorem I told you about. So suppose f is continuous, f being in L2 will do, because then if f is in L2, it has a decomposition with respect to an orthogonal basis, orthonormal basis of polynomials. Then f composed with cosine is positive definite on the Hilbert sphere if and only if you get this expansion. And all the coefficients are non-negative. So that was Schoenberg's theorem. And of course, because cosine is 1 to 1, you sort of free it from the sphere context and you get Schoenberg result on positivity preservers. If f is continuous, then f preserves positivity in all dimensions if and only if f is of this form. So that was his theorem, but that comes from studying metric geometry, Euclidean spheres, functions that are positive definite on them, and so on. It's a very, very pretty story. Yeah, so that's one. So that was one thing I wanted to tell you about. That was sort of the classical part of it. And now for some modern, well, not yet, after this slide, some modern results. So Rudin, as I said, removed the continuity. Schoenberg proved it for continuous functions here, and Rudin said, I don't need that. So he was coming from harmonic analysis, and he was working with Jean-Pierre Cahan, Henry Helson, Katznelson on sort of some kind of Paley-Wiener theory and so on. I'm not an expert in that. So on the circle, he studied preservers of positive definite sequences. And in fact, this notion preceded positive definite functions. So Kara-Theodori and Herglotz and these people were studying PD sequences. So that the idea is you take a positive measure on the circle, look at its Fourier-Stieltjes coefficients, and and if the measure is symmetric, you get real coefficients, and that's what we are calling here positive definite sequences. And so there's a theorem by Kara-Theodori and Herglotz. Their work shows that so if you have a real sequence, then that is such a sequence if and only if this Toeplitz kernel is positive semi-definite. So you write down the Toeplitz matrix based with those entries, and that should be positive semi-definite. Okay. So what Rudin was saying is the following. Suppose I start with a positive measure on a circle. I get the sequence of the Fourier-Stieltjes sequence. I act by my function on each of those sequences, on each of those entries, each of those coefficients, and I get a new sequence. Which functions guarantee that the new sequence is also the Fourier-Stieltjes sequence of another positive measure on the circle? So it's kind of which are the endomorphisms of the space of measures, or that kind of thing. So, and actually again, so what Rudin was really showing in his paper, just like what Schoenberg was really showing was spheres, Rudin was really talking about these things. So F preserves PD sequences, in other words, Toeplitz matrices, if and only if F has the same exact form, power series with non-negative coefficients, the same form. And not only that, he showed that it suffices to work with measures, positive measures on the circle with 3 points or less support. The size of the support governs the rank of the matrix. So what he's really saying is, to prove Schoenberg's theorem, to get that F is a power series, I don't need F to be continuous. I don't need F to act on all matrices of all sizes. Just the Toeplitz matrices of rank at most 3 of all sizes. That's a much, much smaller set. So it's a much stronger result than Schoenberg's theorem, if you will. Right? So so what we looked at was we looked at a different locally compact abelian group, the real line, which is another equally well studied group. Then in that case, for positive measures, you don't have Fourier coefficients in some sense, you have what we call the moments, right? So we looked at the exact same question. Given a measure, positive measure, let's say on -1, 1, there's a moment sequence. Now classify the moment sequence transforms, which take the moments of one measure to the moments of another measure. Again, which are these endomorphisms, if you will. And so this is a parallel result to Rudin. And so let me tell you both the results side by side, or well, one above the other, because they look exactly the same, well, almost exactly. So and now just like Rudin, we can work with -1, 1, or you can work with -5, 5, you can work with the whole real line, you decide what you want. F preserves, no assumptions, again, that was Rudin's theorem. F preserves the set of PD sequences if and only if F preserves positivity on the Toeplitz matrices of rank at most 3, so far smaller test set, if and only if F is analytic and has non-negative Maclaurin curve. So F is of that form, polyazigo form. Okay. And parallelly, what we showed a few years back is you replace PD sequences with moment sequences. So you work with the different star semigroup. Replace Toeplitz with Hankel, because moment sequences give rise to Hankel matrices, and the same third characterization. So again, what this is saying is this is again a far smaller test set than Schoenberg's original result. So what I want to tell you maybe in the next few slides is sort of to go over the proof of this maybe, or some of the key steps in the proof, which again involves some very classical results actually. So before that, now let me get to sort of fixed dimension results. So the idea in the next few slides is to go from a result by Loevner to the result of Vasudeva to the result of Schoenberg, but all of them with these far smaller test sets, rank 3, rank 2 Hankel matrices. So the results are the same kind of conclusions, but the assumptions we need are far weaker. Okay? So, but first of all, a natural question you might ask is, I know now whatever, I know Schoenberg's theorem, Vasudeva's theorem, Rudin's theorem, all of these say that if you preserve positivity in all sizes, then I know what the function looks like. It's a power series with positive coefficients. That's just from the Schur product theorem. The next natural question is, can you fix the dimension and answer this question? And so it is known for 2 by 2 matrices. Vasudeva in the same paper worked it out. And the reason why I say 2 by 2 is significant is because 3 by 3 is still open. So even now, 40, 70, however many years later, we don't know anything more than 2 by 2. Well, we know partial results, but we do not have a full characterization for 3 by 3 or bigger. Essentially, there is only one result for a fixed dimension, and that's due to Loevner. So it actually appears in the paper of his student, Roger Horn. So here is the result. Suppose I is, let's say you only work with positive matrices, matrices with positive entries, and F is continuous, Loevner assumed that, and preserves positivity in a fixed dimension, then F is automatically n minus 3 times differentiable. That's part 1, and all those derivatives are positive. That's part 2. Okay. And if you know further that F is smooth or maybe just sufficiently differentiable, then F is also n minus, then all the derivatives are positive up to order n minus 1. So the first 0, 1, 2, 3, the first n order derivatives are positive, non-negative. Okay. So this is the paper this is the excerpt, an extract from Roger Horn's paper. And so he says that, so this is the Schur product theorem. This shows that all the monomials preserve positivity, and it's natural to ask what other functions do so. Loevner has found in an oral communication certain necessary conditions, and then he states the theorem. There are some more things there, but what I want to tell you about is this part. Just if F is in fact a smooth function, then F has positive derivatives of that order. And you cannot have positive derivatives of the next higher order. That you can check. Just by looking at power functions, you can check that this is sharp. Okay? Great. So let me tell you first of all that we can strengthen this result in the following sense. You don't need continuity. Just like Rudin, we remove the word continuity. You can work locally, so you don't need to say 0 infinity. You can work on a bounded domain. And you don't need to work with matrices of all sizes. Of all ranks. Right? So let me define a special Hankel matrix to be something of this form. Clearly this is rank less equals 2, and this is the moment matrix of a measure with mass A at the point 1 and mass T at the point X. And that's all there is. This is just a moment matrix of a real measure. A 2-point measure, rank at most 2. So suppose F preserves positivity on P2I and on these special Hankel matrices of a fixed dimension n. Then the exact same conclusions as Loevner's theorem hold. Yes, that's the result. I want to tell you one nice, so the point was this entire thing depends on a linear algebra calculation, again done by Loevner, which Roger Horn wrote out. So I want to do the same for you. Yeah. So suppose F is smooth. So I'm assuming that F, I'm only going to tell you the smooth case. And F preserves positivity applied entry-wise in a fixed dimension. Why are these first n derivatives non-negative? That's the question. Right? So induction for n equal to 1, there's nothing, because then it says that F preserves positivity on 1 by 1 matrices. 1 by 1 matrices are positive means the function output is positive, which is what it's saying. So that's just trivial. Now suppose F takes special Hankel matrices to Pn, and therefore if you look at the form of this matrix, if you look at the top n minus 1 by n minus 1 part, then that is exactly a special Hankel matrix of a smaller order. And so it does the same thing for n minus 1 by n minus 1 matrices. So by induction, I already know this much. I already know those things are non-negative. How can I prove that the next derivative is non-negative? Okay, I have. So, so what what Loevner did was he said, I'm going to say that the product of these guys at any point, so for all a, 0, he said I'll prove that the product f of a, f prime of a, f n minus 2 of a, f n minus 1 of a. I'll prove that this is non-negative. Therefore, I should get, by cancelling all of these, that the last term is non-negative as well. Of course, that you can't assume because these are non-negative and not positive. So then you do something very nice trick that he did. Look at f epsilon, which is just add a small multiple, perturb it by a power of just a pure power function. Then, of course, these things also, so if f preserves positivity entry-wise, then by the Schur product theorem, this plus this also works in a fixed dimension. And now f epsilon satisfies the same property, but these derivatives are strictly positive and on any number a. So if I write down this thing now, then the claim is that I can still prove this. Loevner wants to prove this, and then these are all positive, so cancel them and you get what you want. That's what he proved. So now let me tell you his clever determinant calculation. It's literally determinant and L'Hopital's rule. Okay? So choose some special Hankel matrix and look at this function. F epsilon, as we said, preserves positivity in a fixed dimension. So this determinant applied to this matrix is positive, non-negative. And so if I divide it by any power of t for a positive number t, this is, everything here is positive. A is positive, t is positive, x is positive. So all powers of t, then this is non-negative. Right? And I choose my power of t to be, or Loevner chooses his power of t to be n choose 2. Okay? I'll point out that the fact that x is not equal to 1 will play a role later, but and now what he says is, he computes, so look, this is a smooth, so since f was assumed to be smooth, this function is smooth, and so the entire determinant, delta of t is a smooth function, and so Loevner literally calculated the derivatives at 0, and he checked that all of these guys, until the first n choose 2 of them were 0. Therefore, you can use L'Hopital's rule and say, well, if I want to say this is non-negative, then the limit is non-negative, start taking derivatives. Just take derivatives one after the other. So that limit equals this limit, keep going, you get to this limit, and because f is smooth, this is smooth, so by continuity you just get this. So I get this number, whatever this number is non-negative. And then Loevner actually calculated this number as well, and this is the value. So he explicitly did this calculation, some multinomial, and this is where I use the fact that x is not equal to 1, so this is a strictly positive number, and all of this. And so I get that all of this is non-negative, this product, and therefore what I want. And so that's how Loevner proved this, that the first n derivatives must be non-negative by induction. Okay? So it was a very, very clever and a very beautiful calculation. The nice thing about this calculation is actually, the nice thing for me, is that Loevner did not compute one more derivative, because if he had computed one more derivative, he would have found this amazingly beautiful family of symmetric functions sitting inside here. And luckily he didn't. That family sits inside here as the symmetric function for capital N is the 1 function. And so but nobody notices the 1 function. If he had done even one more derivative, there would be a non-trivial polynomial, and then you would find out what happens. So the point is, Loevner's calculation first of all looks like it's analysis, it's derivatives. No, it's completely algebraic. and can be made so. Instead of derivatives, you use derivations, and you can make it work over any commutative ring, and that leads to actual symmetric function identities. And this time, so analysis is contributing to new algebra identities. That's the very nice and satisfying thing maybe about Loevner's calculation. It has in its it has in its germs, I forget what the use is, but the seeds of new symmetric function identities. And it was also useful in classifying a new set of polynomials, finding new results about functions, preserving positivity in fixed dimension. I'll just point out a little more of history. So Loevner actually, so remember Roger Horn's paper was in 1969. So Loevner actually had summarized these calculations even earlier to Josephine Mitchell. And so I used to actually work at Stanford before this. So Loevner was at Stanford. So when he passed away, he bequeathed all his papers to the Stanford Library. And so at one point, I and a collaborator of mine, we went and dug them out. And this is Loevner's own handwriting. So he says, when I got interested in the following question, let f be a function defined in some interval, consider real symmetric matrices, n by n, with elements from that domain. Which properties must f satisfy for the entry-wise transform to be positive semi-definite? And I found as necessary conditions that if f is n minus 1 times differentiable, then exactly these derivatives must be non-negative. Okay? And he says why this is sharp. This does not work for power functions. Otherwise, higher derivatives. The proof is obtained by considering matrices of this form, and then you do some calculation, look at the Taylor expansion. The first term in the Taylor expansion that's non-zero is this product of the derivatives that I told you. So this is exactly his proof in his handwriting, if you will. Okay. And so finally, to conclude the theorem of, so this was to prove the Loevner theorem about functions preserving positivity in a fixed dimension. And then I promised you, if you look here from Loevner to Vasudeva, so now I want to tell you about functions preserving positivity in all dimensions, but on matrices with positive entries. Okay, so the point is, using modifiers, one can prove that if you know it for smooth functions, then you know the result for continuous functions. I told you the result for smooth functions, so we know it for continuous functions. And then there is not really a result of Ostrowski, but a Banach space variant of that, which shows you that using some properties of mid-convexity, every such preserver anyway is continuous because of P2. And so that's why one obtains the Loevner theorem. And now from that you can prove the Vasudeva theorem. So the following are equivalent for any function acting on 0 infinity or 0 1, you take your pick. F preserves positivity on all matrices of all sizes if and only if F preserves positivity on these special Hankel matrices, rank at most 2, if and only if F is a power series of the desired form. So these are all if and only if. So clearly 3 implies 1 is just that Polya-Zigo observation from the Schur product theorem. 1 implies 2 is obvious because this is a smaller set of matrices. Vasudeva proved that 1 implies 3. So if you work with all matrices of all sizes, then you get this. And now what we can say is actually 2 implies 3 is already there. So 2 implies 3 is, but both the proofs are exactly the same, Vasudeva's or ours. The proof is that by the stronger Loevner theorem, or in Vasudeva's case by the Loevner theorem, if you will, F is smooth and all the derivatives are positive, non-negative, so you can extend F to the origin and apply Bernstein's theorem on absolutely monotonic functions. Right? Okay, so that's not too hard once you have Bernstein's theorem. Yeah, so that's why you have the theorem for matrices preserving positivity on, functions preserving positivity on matrices with positive entries. And now what about going back to the full Rudin and Schoenberg result? So in that case, you use something which one of my co-authors is a big expert on, of course. He's also an expert on moment sequences. So positivity certificates for limiting sum of squares polynomials on compact semi-algebraic sets. That's a big thing. So by some kind of integration trick, which actually you can find in Achizer's book as well. It was known to Markov and so on. One can use that trick to show that F is continuous. So that's the first step. The second step is if F is also assumed to be smooth, then you can show it's real analytic. But now if F is assumed to be smooth, then by the previous slide, by the Loevner theorem and Bernstein's theorem, F is a power series on the positive side. F is real analytic on R. So by the identity theorem, F is a power series on everything. Okay, so that's the step 2. So I know it for smooth functions. I can prove it for continuous functions. So I know my function is continuous, but I know it for smooth functions. How do I get from smooth to continuous? Modifiers. And so you finally use modifiers and finish the proof. And the point is, well, there's a typo here, first of all. Second of all, I want to point out that the same kind of thing, actually the one-dimensional case can be used as the base case in an induction to prove the same theorem for multidimensional functions. So functions acting on tuples of matrices or moment sequences, tuples of moment sequences, and taking them to a moment sequence of one measure. Okay. Okay. So in the last few slides, then, yeah. So and again, in that case, the result for acting on all matrices of all sizes was worked out by not Roger Horn, but 3 other students of Lovner and Carlin. So Alan Pincus, Charles Micheli, and Carl Fitzgerald, who was at San Diego. And they proved it for all matrices of all sizes. Again, with Belton, Guillot, and Putinar, we proved it for only tuples of rank at most 3 Hankel matrices of all sizes. And the same exact statement holds. It's a power series. It's multi-entire with non-negative Taylor coefficients. Okay. Okay. So let me tell you quickly then. So yeah. So as I said, classifying the. Okay, I think I'll have to probably skip a little bit. So I'm going to skip this, but what I'm going to say is that if you look at just polynomials that preserve positivity in a fixed dimension. So if you look at matrices of all sizes, then you know that all the coefficients have to be positive. That's the Schur product theorem or Schoenberg's theorem. So if you want to preserve polynomial positivity of a fixed dimension, you should expect that since there are much smaller number of matrices to work with, you have many more functions that work. And yet until sort of very recently, there was not a single example known with a negative coefficient. So you should expect there to be examples with negative coefficients. They were not known. And so sort of with Belton, Guillot, and Putinar, we solved the baby case 3 years ago. And then with tau, we worked out sort of much more general results. Again, what is interesting is we again need to use rank less equals 3 Hankel matrices. They sort of do the trick. And the proofs are even more interesting because the proofs use sort of representation theoretic tools, symmetric function theory or algebraic combinatorics or representation theory, whatever you want to call it, something from mathematical physics as well maybe. And it's really the mixing of these 2 areas that led us to this thing, which was particularly satisfying for me because I started out in representation theory. I still do a bit of it and also positivity, so I could mix both of them.
Is this where you took one more derivative?
No, so these give me special cases of the thing where I took one more derivative. And so what the claim is that the 1x has, so where is this? You can look at these kind of things. Determinant of some function applied to a rank 1 matrix. If f is a power series or polynomial, you get some kind of polynomial identities using Cauchy, Binet, and so on. If f is a formal power series, there was sort of only one such identity known, which was for fx equals 1 over 1 minus x. Actually, I should put a t here. These are constant, t is a variable, and I should take. So now this is a power series itself. You can calculate the coefficients by taking derivatives, and for this one, which is 1 plus t squared plus so on, this was what is identity by Cauchy, Cauchy's determinant identity, and there was a generalization by Frobenius. He had an identity as well, and that was all that was known. And what I can do now is I can answer this question for any power series. And for that, you need to extend the calculation by Lovner and take derivatives. Okay, so let me give you okay, that's my penultimate slide. So the key ingredient, as I said, was this symmetric function. So the idea is take a bunch of integer powers, look at this generalized van der Waals determinant. It's an alternating function. Divided by, if it's an alternating polynomial, these are integer powers, then it should be divisible by the basic alternating polynomial, the van der Waals determinant, the usual one. So divide it out, that's a symmetric function in the variables u1, u2, un. And so for example, if I take u1 to the k, u2 to the l minus this thing, then you get a geometric series. That's all there is to it. And this is a very nice and well studied basis of symmetric functions. So what we do is we treat Schur polynomials now as functions. This is analysis, so we treat it as functions, not just algebraic polynomials, and where all the u's can be positive all the u's are positive numbers. So if you look at this function, all these are sums of monomials. So if you increase the value of any of the coordinates, the value will go up clearly, right? Now what we claim is that using some deep results in representation theory, the ratios are also coordinate wise non-decreasing, and that allows us to, combined with the Harishchandra integral, find a new characterization of inequalities of weak majorization. So suppose m and n are n tuples of what we call powers, and now you can extend from integer powers to rational powers, and rational powers by continuity to real powers. So suppose m and n are n tuples of real powers, then this is the definition of the Schur polynomial, this divided by the usual van der Monde kind of thing. Anyway, so if you look at this generalized van der Monde divided by the van der Monde of the matrix, so product mj minus mi, and if that dominates this thing for all u in this part of the positive orthon, that is if and only if the tuple m weakly majorizes the tuple n. So if m and n were actually integers, then you could divide both sides here by the van der Monde of the u's and get Schur polynomials. And so but this is much more general because it works for not just integer powers but real powers. Okay, so that was sort of one part of the paper with tau, among other things that we did, but we found a new characterization using representation theory tools about weak majorization. So as I said the previous time, Lovner's calculation connected analysis to new results in algebra, and this is somehow going the other way. We are using algebra or Schur polynomials to get new characterizations of inequalities. Okay, thank you very much. References.
Thank you very much. Anyone have questions or comments? Barry?
Did Lovner, so this was a copy of a letter Lovner sent. Did he use carbon paper, or do you think he did it by hand?
Well, he clearly wrote it. That seems
No, but it could be carbon paper. The question was, did he make a copy by using carbon? Could you tell? Was he using carbon paper, or did he do the copy by hand? It's just
I have a picture. I have the photograph on my laptop, so I can show you the photograph if you can deduce something from it.
It's a natural question.
Yes,
right?
yes,
Did
yes,
he
yes,
actually rewrite every letter he wrote by hand?
Good question. Good question. He of course must have kept a copy to show Roger Horn 2 years later.
He probably kept copies. Yes.
Actually, no, that was the year before he passed away, I think. Roger told me he passed away in 68, Lovner. So this was almost at the end, and Roger's paper came out in 69.
But I'll bet if he
No.
I bet he did this when he was 12. I mean, I don't think he just started in
No,
his old
sure,
age
absolutely.
keeping copies of his
No,
correspondence.
I'm sure he kept copies.
I'm just
Well,
curious whether
would you know if, when you saw people in the late 60s, did you see if
Yes, the carbon copy are much decorated. You know, it's a
Well, that's
How
why
old
you
is carbon
look.
copy?
If you saw it, you might be able to tell if it was a carbon copy.
Oh, was
But
the
by then
paper
car-
sort of
But by
dirty?
then, carbon copy was pretty good.
was it?
Because,
I can show you the
the
photograph if you can,
amazing
yeah.
story I know is that when Kato's famous paper with Kato's theorem,
Mhm.
he submitted it to the journal and they lost the paper. He had to so he somehow had to copy it over. But some people didn't do this. So there's a famous book by Wigner and Eisenbud, which is very thin. It was supposed to be much thicker, but they lost the manuscript twice.
Twice.
And so by the time the final manuscript just was
That's a
much
shame.
shorter. So one doesn't appreciate modern technology,
Absolutely.
even Xerox machines, let alone tech.
Yes, no. Even later, I mean, yeah, but Xerox, I'm very thankful to be
And of
working
course-
when I do.
But this trick you showed with adding epsilon x
Yeah,
to
yeah.
n, Lovner, or at least other people, use the exact same trick
sure.
on monotone matrix theory.
Aha. So that must show up in your book.
Of course, it's used all the time.
In how many of the 11 proofs?
What?
In how many of the 11 proofs, if you can remember?
I don't remember, but
Just
the
joking.
point is that you use
Yeah,
the
yeah, yeah.
fact it's enough to suppose something
Right.
certain. And it's sort of remarkable that in Lovner, in the monotone matrix, you get derivatives up to order 2n minus 3 instead of n minus
Aha.
3.
Okay.
There's an extra 2, and it's sort of strange that
Well, there's an extra n, really.
that's what I think.
Yeah.
But somehow Lovner
No, yeah, that was his game.
Lovner was a remarkable.
That was his game. Yeah, this whole thing was his game. Definitely.
Okay, thank you. Any other comments people would like to make or questions? Yeah.
Well, I'm not sure whether I have missed some point in your lecture, but this is about some kind of a converse of one of your results. See, suppose you know that a function
Sure,
has
correct. Yeah.
positive derivative up to certain order.
Yes.
Then can you say anything about positivity preserving properties of that function?
If it has a positive derivative up to certain order. You're asking for the converse of Loebner's theorem.
Right.
I don't particularly know. I don't know actually. I'll have to think about it. Certainly for power functions, that sort of is a characterization. So if the function is known to be a non-integer power function, then that's kind of a characterization. But for more general classes, I don't know.
Okay, if there aren't any other questions or comments, we have a coffee break until 3:30, and let's thank the speaker again.
Thank you.